so that one lasted all of 10 seconds. Okay, so let's see if this is any better. It does seem to be moving more smoothly for me. Hopefully that's the case for you guys. Let's see. Let's just type it out just in case. Oh my gosh. So this seems to work for me, so we'll see if people can tell if it's better or not. If not, we'll start at the top again. Awesome. Okay. Weird. Who knows? Well, seems to be working. It's working for me too, so we're good. Alrighty. So with that in mind, I will start over, I suppose. We're starting chapter 11 today. We have just a few days left. This will be our last chapter. There's not going to be a specific homework assignment on this, so you'll just have the lab sim, but I will put practice problems up for you to take a look at. So there's not going to be any kind of like anything that I'm collecting for this. So I have your 5 homework assignments still to grade from who knows when. I'll take care of those, but you're not going to have anything left to turn in this semester aside from your final exam and I think one more lab, and that's it. With acids and bases, let's go ahead and get started then. So again, no homework on this, but it is on your final, and it is more represented than the other topics are. Everything is kind of equally distributed, except kind of acid base gets twice as much, if that makes sense. So we have 11 chapters or so. So imagine kind of every topic gets 1 out of 11, basically, and then this one gets 2 instead. So it's a little bit more represented. Anyways, so if we want to first talk about acids and bases, we're going to need to define what acids and bases are. And so old Greek guy Arrhenius defined acids as substances that generate H plus in solution. And so we have some examples here. Let's look at the first 2, where we have our kind of standard aqueous acid. And it's breaking up into H plus and whatever anion that it was made with. So this definition is, it's still something that we teach, even though it is a little bit restrictive in that it forces us to have in solution as part of the definition. So that's why we have to put aqueous on these acids, is that when we're describing them as Arrhenius acids. That's kind of the most specific one. And we're going to see that in chemistry we actually have other definitions that we use a little bit more often, just because they're a little bit more broad, especially when reactions don't take place in aqueous solution. If we're going to be having them take place in organic chemistry, that's a huge component, acid-base chemistry of organics, and that stuff is not done in water. So how can you call things acids if, if your definition says it has to be in solution? All right, well, anyways, so it may be more accurate first to write that the actual acid is combining with water to form hydronium in your anion. That's a little bit more accurate because we don't just have H plus floating around. H plus is just a proton, and we don't have subatomic particles just flipping about solution, just zipping around. So it is more accurate to write hydronium. That extra hydrogen atom or nucleus is stuck onto a water molecule. That's more accurate of what's actually happening in solution. But since we are lazy chemists, we will typically write it just as like kind of that first line. We'll write H plus. It's just a little bit easier that way. So we do that. So just keep in mind that in reality it's really H3O plus, but that's okay. We don't need to worry about that. Conversely, Arrhenius said that bases will generate OH minus in aqueous solution. So something like sodium hydroxide. Strong electrolyte will break up into sodium ions and hydroxide ions. So you're going to see that many of our hydroxides would follow under this base idea. But we're going to see others like ammonia actually that's it, will generate OH minus as well. So something that doesn't even have OH minus as part of its kind of idea or its identity can still form OH minus in solution. And so that's kind of the opposite here. So we're going to say that H plus and OH minus are kind of opposites that we're going to deal with. But this definition is kind of old and less useful to us. So enough of that. Let's talk about another definition. The Bronsted-Lowry acids and bases, or definition we'll say, are quite a bit more useful. So this Arrhenius definition talks about things dissolving and breaking up into H plus or OH minus, right? But the Bronsted-Lowry definition, as we're going to see, talks about how things behave in reactions. So this is how acids and bases behave. Rather than something physical like dissolution, we're going to actually look at chemical reactions. And we're going to see that an acid is the the substance that donates H plus to something else. And a base will be the opposite. It's a substance that accepts a proton. H plus is a proton, right? The hydrogen atom is just a proton and an electron. If it loses the electron, it's just a proton, right? So you'll often hear people just say proton instead of H plus. I guess a little bit easier to say. And so the bases will accept protons. And so this will actually still kind of work with our previous reactions. If we take a look at that first one we did, we took hydrochloric acid, put it with water, we made hydronium and chloride. And so if we want to see which one's acting as the acid and which one's acting as the base, you always want to kind of look at the anions here. If we kind of just look at the products and reactants, we see that one of them is, they're kind of making pairs, right? You can see that the water is very similar with the hydronium, and the HCl is similar with the chloride, right? The only thing that's different is the H's. Over the course of the reaction, we see that HCl loses H plus over this reaction. It becomes Cl minus, so it's lost its H. Therefore, we're going to call it the acid. It's something that has given away, donated its H plus to something else. And so HCl will be our acid, which we probably already knew because its name is hydrochloric acid. So hopefully that one is not crazy, right? We do see that water gains a proton. That means it has accepted it from the HCl. As a result, water will be our base. And so, as a result, we're going to see, just like with redox stuff, these are going to come as pairs. So they're going to come together. So if you're going to have an acid, you need a base as well. So something, if you're going to have any sort of Bronsted-Lowry definition, that is, you have to have a reaction that's happening. Something has to give away an H+, something has to accept an H+. Let's take a look at that ammonia one. Take a look at this. Again, hopefully we can very quickly identify our pairs. We see that ammonia is more similar to ammonium than it is to hydroxide, and water is more similar to hydroxide. Here we can see that ammonia will gain H plus over the reaction. It's now NH4 plus, so it has taken in an extra proton. That means it's the base. It has gained a proton, it's the base. And we see that water has lost H plus, and therefore it's the acid. Right, so we see that, just to kind of confirm, that's NH3 turned into NH4 plus. We can see that it has gained a proton, and H2O, we can see here that it has lost a proton. It has lost H plus. So just like with redox, we've got one thing gaining electrons, losing electrons. In this case, now we're gaining or losing protons. So that's the only difference here. And so we just have different names for them. And so instead of talking about oxidizing agents and all that good stuff, we just talk about acids and bases. So there we have it. If we want to notice something, in these two reactions, the first one we have water acting as a base. The second one we have it acting as an acid. We're going to see that we have a special name for these, actually two names. We're going to see substances that can act either as an acid or a base. These are called amphiprotic or amphoteric. So there's our fun vocab lesson for the day. So these words do actually have slightly different definitions, but they're not important until you talk about the next definition of acids and bases, which we don't cover this semester. So for now, these two words mean the same thing. They just mean they can act as either an acid or a base. All right. We'll do a couple of examples here, but do we have any questions on these first ones? And how is the stream going? Is it like, I mean, I'm looking at it, I guess, on my other monitor. It seems to be working this time, where it was flickering last time. So, are we okay so far? Cool. All right, let's take a look at one that's not so perhaps obvious to us. Here's an acid-base reaction. If we look at these, we're we're looking at pairs here, right? We want to see what's similar on each side. So hopefully we can see that the dihydrogen phosphate and the hydrogen phosphate are a pair. And hopefully we can see that the bicarbonate and the carbonic acid, are pairs. Although I'm not writing in here, this would break down. We would see the bubbles and all that fun stuff. But for right now, let's not worry about that. Just identify our acids and bases right here. So, if we look at the first pair that we have, we see it has lost H+. If it loses it, that means it's the acid. Or here, let me write that on that side. So our dihydrogen phosphate there is our acid in this reaction. And then if we look at the other one, we have the bicarbonate. We can see here it has gained H+. It now has 2 hydrogens where it had 1 before. That means it's the base. All right, so we have transferred a proton from our phosphate to our carbonate. Hooray. Now, what if I told you, insert the Morpheus meme here, this reaction can happen too. Let me write it in a slightly different way. This reaction could totally happen the opposite way. And if we take a look at it, we'll say, okay, well, we have carbonic acid. Hint, there's the name acid in its name. Turning into bicarbonate. That has lost H+. Therefore, it's the acid. Our hydrogen phosphate becomes dihydrogen phosphate. It gained H+. Therefore, it's the base. Oh. Notice before that this was the acid in the last reaction, and now it's a base. And you'll see that it's exactly the opposite. So this one used to be, the base, and now it can act as an acid. We call these our conjugate pairs. If we take a look at that, if I take our original reaction and attempt to paste it, there we go. And let's get rid of these, oops. We saw that in the forward reaction, the reaction going in the normal direction, This was an acid, this was a base. But if we turn that reaction around, now we have carbonic acid being the acid, and our hydrogen phosphate being the base. And so, because what we typically would see this, by the way, represented with this special type of arrow that unfortunately we don't talk about in this course, though I think we should, but it's not on our list of topics. Suffice to say, this reaction can go back and forth. So it goes both ways. And as a result, we can see that in one reaction going forward, we have our acid and base. But if we go backwards, we have a new acid and base. And so just for purposes of kind of clarity here, because both of these can go, these reactions can happen both directions, back and forth, we'll call just one of them by a special name. We'll call this one the conjugate acid. And this one will be the conjugate base. So that just means it's on the other side of the reaction from what we started, and it can act as the opposite of what it used to be. So, for example, bicarbonate is a base in our forward reaction. Once it has accepted that proton, as a base would, it now is carbonic acid. And carbonic acid can react as an acid, and it's even called an acid, right? So just for clarity, we call it the conjugate acid. And so in this reaction that we've written here, carbonic acid is our conjugate acid. It means it will be the acid if the reaction goes in reverse. And hydrogen phosphate there is our conjugate base. It can act as the base if we turn the reaction around. So just identifying pairs. Your conjugate acid will be whatever your base used to be, plus an H plus. So let's take a look at that. So base plus your hydrogen equals conjugate acid. And it'll be just the opposite here. So acid minus H plus is your conjugate base. So if I were to ask you, what is the conjugate base of water? Well, if we're looking for the conjugate base, that means water must be acting as an acid, right? So we can say H2O minus H plus will give us our conjugate base. And so if we subtract both a hydrogen and a positive charge from this, we'll get hydroxide. And so we say that hydroxide is the conjugate base of water. What about oxalic acid? What's its conjugate base? Well, we can go ahead and make a huge mess. If we subtract an H plus from this, we had 2 protons before. Now we have just 1. We subtracted a positive charge, meaning now we have a negative charge. We had a neutral one, we lost a positive charge, so now we're a little bit negative. and so it would be hydrogen oxalate here. We just look at one proton being transferred away, by the way. We don't look at multiple. Even though oxalic acid is diprotic, it has 2 protons. We don't care. Its conjugate base will just have 1 proton. We could also have, we can go further. Well, that we can go ahead and take another one off. But now we're looking at the conjugate base of hydrogen oxalate instead of oxalic acid. So oxalate is the conjugate base of hydrogen oxalate. It is not the conjugate base of oxalic acid. Conjugates are only different by 1 proton. So either they'll have gained it or lost it, but there's only 1 proton difference for a conjugate pair. If we take a look at the opposite one, what's the conjugate acid of, what shall we do? No. Of cyanide. To find the conjugate acid, we would just add a proton, and we would get hydrogen cyanide, or potentially hydrocyanic acid, depending if we're aqueous or not. We're going to see that very often these things containing nitrogen can act as acids and bases. Conjugate acid of So if I tell you that it's the nitrogen that's going to gain the extra proton, carbons don't ever gain protons, but nitrogens can. Well, we can do that. We would get CH3 and H3 plus. So just so we understand this, nitrogen and oxygen can accept H pluses, but carbons cannot. Nitrogens are more likely to accept. The reason for that if we look at something like methane, this will not react with acid because that carbon already has a full octet. It's already happy, right? Putting an extra hydrogen on it would give it 10 electrons now. There would be nowhere for it to work, so not going to happen. If we look at ammonia, though, and give it a proton, we get the ammonium ion. We're going to see that what happens is that lone pair on nitrogen can go and snatch up a hydrogen, giving us ammonium overall, which we see quite often. Ammonium is pretty stable. Water can also take a proton, That will give us hydronium. That's, again, typically what we would see in reality. It'll be the same idea. We'll have a lone pair go and snatch up a proton and form a bonding pair instead. And now we have hydronium. But oxygen is more electronegative than nitrogen. And so it has a harder time being positive. So you don't typically see hydronium very often. Like, you can go to the store and you can buy ammonium nitrate or ammonium chloride or something. You can buy it. NH4 plus is stable. Because nitrogen is less electronegative, it can kind of handle that positive charge a little bit more. But oxygen is more electronegative. It does not want to be positive at all. So you can't just go and buy hydronium chloride or something. It doesn't work like that. You can't go and buy hydronium nitrate. These things just don't exist. Mostly because each would just be popping around because it's not as stable. So we're going to see that nitrogens, the point of all this was things that these will act as bases. So nitrogen typically are things that can act with bases. If you've taken biology, you know that DNA is made of sugar, phosphate, and a nitrogenous base. Those bases are nitrogenous. They have nitrogen in them that can act as a base. So we're going to see that. That's the whole point of talking about this stuff. So nitrogen with its one lone pair and relatively low electronegativity can go ahead and snatch up a proton and it'll be happy. So we're good with that. All right. Any questions on that? All right. We're going to see that the reason that we had those 6 strong acids that we talked about in the solutions chapter, which we'll go over again, they form extremely weak conjugate bases. For example, this reaction cannot go backwards, which is why we consider hydrochloric acid a strong acid. It dissociates completely. It does not go back again to form HCl. Once they've split up, that's it. They're done. They're off doing their own things. They're done. So this chloride ion is too weak to act as a base. It is a negligible base. All right, and then we're going to see conversely, if we take a look at something else, actually I need to, let's put it with HCl, why not? Oops. So just so we can see the how do you make HCl? So HCl occurs as a gas typically. You can take it by combining hydrogen and chlorine gases together with a little bit of energy. You can make it, no problem. But remember that when we talk about HCl solution, we don't remember that HCl being a strong electrolyte does not exist as HCl. We already take it as having split up. So remember that for strong electrolytes, they are completely split up in solution. So the HCl that you can buy as hydrochloric acid is not really HCl. It's H plus and Cl minus, just dissolved in solution. However, HCl, hydrogen chloride, does exist as a gas, but that's not something that's an electrolyte because it's not dissolved in water, right? So you can have HCl gas, hydrogen chloride. You can make it from hydrogen and chlorine. There's a whole bunch of other ways you can make it. But as soon as you put it into water, it's going to break up. And so even though you'll typically see a bottle that's labeled hydrochloric acid, what it really means is that you have those guys floating around in there. And of course there's waters and all that interacting with them. So, you know, this bottle might say hydrochloric acid, but really it's hydrogen ions and chloride ions. And as you can imagine, it's a little bit easier to write hydrochloric acid on a bottle or to just leave it as HCl rather than talking about the behavior of it. So that's why it's typically done. So that's how. Alrighty, so with this, let me hop back here real quick. If we look, NaOH is going to be a strong base for us because water is a very weak acid. Normally, when we think of water, we don't think of it being an acid, right? We don't really call it hydroxalic acid, even though we could, because it's a very weak acid. We're going to see just how weak in a little bit. But we're going to see, first off, just understanding that the conjugates of things that we call strong are very weak. So NaOH is a strong base. It has a very weak conjugate acid. And so you're not going to see this reaction go in reverse. You're not going to take salt water and get out HCl out of it and sodium hydroxide. It's one directional only. We're going to see, though, with weak stuff, when this guy breaks up, it can definitely go backwards. And remember, we saw this when we talked about, we did some stuff about the electrolytes, right? We saw that acetic acid was a weak electrolyte. It does not really conduct electricity. And we'll say that maybe it's, 1% ionized or 5% ionized or something. So that means 95% of the molecules are still Hc2, H3O2, and the rest of them have split up. But the majority do stick together. So this is a stark difference here. So when you actually buy acetic acid, it is Hc2, 3O2, rather than having the ions split up there. So we're going to say that this is a weak acid. As a result, it makes a weak conjugate base. Not an extremely weak one. Obviously, if it were an extremely weak one, then this would be a strong acid. So it's not extremely weak. It's still going to be a conjugate base. But consider that the chloride one is so weak that it can't even act as a base. So chloride will never act as a base. However, acetate can certainly act as a base. It's just a weak base. Obviously, it's not going to be a strong base because then acetic acid would not be acidic at all. It would be a negligible acid like water is. Water is negligible in terms of its acidity, by itself, that is. let's take a look at it. We're going to see the stronger the acid, the weaker its conjugate base is. And vice versa. The stronger your base is, the weaker your conjugate acid is going to be. We're going to see that the ones that we looked at, these are all negligible bases. Those are the conjugates of our strong acids. Remember, nitric acid, hydrobromic acid, hydroiodic acid, hydrochloric, perchloric, and sulfuric acids. Those are our strong acids. Their conjugates are all extremely weak, so much so that we can just negate them. They don't even act as bases. You'd have to have something extremely acidic to react with these guys, because they're really bad bases. And so they just will not even act as bases. We're going to see there's really only one negligible acid that we talk about. We could say that ammonia is also one. Better believe methane. These are negligible acids. Negligible acids. So you're going to see that water is not a very good acid. Ammonia is certainly not a good acid, and methane, forget it. There's no way you're going to get methane to act as an acid. So, not going to work. Alright, so suffice it to say that for us we had those 6 strong acids. We had our 6 strong acids here. Our strong bases that we're going to mostly deal with are hydroxides. Amides, typically we don't deal with very much because they're extremely strong bases, so this is something we'll deal with in organic chemistry. That's not something we deal with here. We don't really talk about amides in this class, so we're not going to worry about that. So for us, strong bases are just hydroxides. So that's the easiest way to do it. We can just say any things with hydroxides are going to be strong bases. So that would be, for example, barium hydroxide and maybe strontium hydroxide, but that's pretty much it. Those are pretty much your only strong bases here, and they're all hydroxides for us right now. In more advanced chemistry, you'll have other strong bases that you'll deal with, but for us right now, it's just hydroxides. And these are pretty much the only soluble hydroxides that we're going to deal with. Calcium hydroxide, which is lime water, is not really that soluble. So it's just not soluble enough to be considered a strong base. All right, so we really only have those 5 strong bases that we'll deal with. All right, one more thing to note. These guys do not contribute to your acid-base stuff. So if you see lithium, potassium, or sodium, you can just kind of ignore them. They're there to charge balance things. That's their only purpose. They're spectators. They don't actually do anything in the chemistry. For example, if you look at the reaction that we just did, we have a strong base we have a strong acid. We have this guy, which is going to be your negligible base, but it is still a conjugate base, it's just a terribly weak one. And then we have water, which will be our negligible acid, which comes from the strong base hydroxide. And so if you were to look at the net reaction here, you don't even consider a chloride. You look at this. You look at that's what you're looking at for the net reaction here. So the net ionic equation gives you hydroxide plus H plus turns into water, and that's it. So chloride doesn't figure in because chloride is just there as a negligible base, doesn't do anything. It's there to balance out the H plus, as it were. Just like sodium is there to balance out the OH minus, sodium is another spectator. It doesn't really do anything in the chemistry. So we're going to see that most acid-base reactions follow this. As their net ionic equation. Sometimes, yeah, you'll have other products or whatever, but by and large, this is kind of like the general template. So you have some sort of acid, some sort of base turning into water. When we talk about most acid-base reactions in this course, we're going to see that this will be your net ionic equation by and large. So that's what we see here. Alrighty, any questions on this stuff? Alright. I think this is actually a good place to stop for today. I will make your kind of practice stuff available so you can practice identifying conjugate acids and bases and that sort of thing, and just taking a look at some of that. So I'll make that visible for you guys on camera so you can start working on that. So again, I'm not collecting anything for acid base, so you're done turning in homework for this semester. So at least for me. Your other classes, who knows? So, all right. If that's it, then I will see you all tomorrow. Enjoy your Tuesday.